Yeah. We'll start with today's live session. So this will be based on the week two uh, topics what sir told you in that NPTEL lectures. So yeah, before that there were some doubts in the week one session. So since these lectures are recorded, like it will be recording, so you will be getting like maybe I don't know, but you will be getting these recordings for your further like again to like view also. So I will be talking about the doubts which were asked in the previous session. So there was a doubt regarding bias current. So there was like how that R1 parallel to R2 concept is coming. So I'll just start with that. Uh, Previous session doubts. Okay. So we have the concept of bias current. So here if we say this is the input voltage and these are the resistances, so there will be some bias current from here and here, IB1 and IB2. Okay, so here we looked at how this bias current is affecting the output. So if we just see its derivation, so let's say the I1, it is the I1 current here, and then I2 current is here, and then we can at this node A, we can write the KCL equation that I1 equals to I2 plus uh, this one, I2 plus IB1. So then we know I1 is what? I1 is V in, the V in voltage, this one, minus V minus, that is the voltage of this one, this terminal, divided by R1. I2 is which is actually V in by R1, because this is 0, because this voltage is 0, so because of virtual short this is also 0. So then we had I2 is V minus minus V naught by R2 at this branch, this branch. So here also this is 0, so we had minus V naught by R2. So if we'll put this in this equation, we will get final expression as V naught equals to minus R2 by R1 into Vn plus R2 IB1. So the output voltage should be this, since this is an inverting amplifier, but we are getting this thing extra. So how to remove this? So for that we will be having one compensation for that. So let's say compensating this bias current, compensating bias current. How we can do that? Okay, so this we can do by achieving, so this basically, so just for the information, this is the week one concept. So there were some doubts regarding this, so I'm just deriving that bias current thing here. So it will be, if we add one resistor here, r, let's say 3, so can it solve our problem of this thing? Can it solve this? Can it remove this thing? Can it remove this? So we'll see. So this was R1, this was R2. Let's say we, for the time being, we neglect this input voltage. We are just taking the effect of the bias currents. So this is IB1, this is IB2 minus plus. Okay, this is V0. So then we had, again we will use that I1 equals to I2 plus IB1 at this node, this equation, KCL equation, node A. So then we have I1 equals to as V in minus V minus divided by R1. So here, since we are not using V in, so it is 0. But V minus, this voltage will be the drop across this voltage, because yeah. So this voltage, so this node voltage at node A is equal to the voltage at node B, and node B voltage is actually the drop across this voltage. So that's why, so it will be minus of minus IB1 R3. So this is basically IB2. This is IB2. Yeah. So divided by R1. Okay. So now what is I2? We got I1. Now I2 is V minus minus V naught by R2, which is equals to. So if you have any questions in between the lecture, you can ask me. Yeah, so I'm saying, if you have any questions in between the, in week one or week two, you can ask me anywhere. Like, you can interrupt me in between, and you can just ask me. So yeah, so I'm just for the ones who just entered. So I'm just telling about the concept of biasing current and how we will remove it. So since this was a doubt in the previous session, that's why I'm telling this. Okay, so this was there. So then, so we were there. So I2 will be this. So we can write I2 as, this will be minus IB R3 to minus V naught divided by R2. So if we will use this, uh, input this in this equation, then the final value after solving, we will get IB, this is 2, this is R3 R1 equals to minus IB2 R3 R2, then minus V naught by R2 plus IB1. So now what will happen? Then this will be like, so since we need this to be 0, so because this is the effect solely because of the bias currents, so that's why we need this thing to become 0. So it will solve this thing. So we will be and we are assuming one thing, that IB1 is approximately equals to IB2. Okay, if that is so, then what will happen? Then this equation will become IB into R3 1 by R1 plus 1 by R2 equal to IB, IB, this one, IB 2, IB, this is IB2, this is IB1. So if this is this, since these were same, so we can say R3 equals to R1 parallel R2. So this is the, so if, so what does it mean? It means that if this resistance, the resistance here, if this is equal to the parallel combination of this resistances, then we can avoid this, we can compensate this bias current. So one another another doubt was there. So doubt was that, I will just write you that question. So one guy from previous session, he asked me that what is the effect of is like, is there any effect, or we'll say, is there any effect of slew rate on the bandwidth of the op amp. So this was also a question asked in the previous session. So basically, like every op amp is having a compensating capacitor. So when we will see the open loop characteristics of an op amp, so it looks like this. So this is because of the compensating capacitor in this. So this is the FC cutoff. This is directly inversely proportional to the C. So this C is the compensating capacitor which is used in the op amp while manufacturing. So this is the open loop gain of op amp. Okay. So now we know that slew rate is what? The change in the output voltage, which we can also say change I by C. How we'll say this? Since we know Q equals to CV. Okay, if we'll integrate this, I will differentiate it with respect to time. We will get C dV by dt. Okay, then this will be I. This is C. This is dV by dt. So from this we got to know. Okay, this is slew rate. So this is slew rate. So now, in order to increase the slew rate, if you want to increase the slew rate, then what we'll have to do? Either we'll have to increase the current, or we'll have to, like, this current should be very high, infinite, or should be very high, or the capacitance we should decrease. So what will happen? Like, this capacitance is related to the bandwidth in this way. So this is the bandwidth. Okay. So now, if we want to increase the slew rate, then we will decrease the capacitance. What will happen? This capacitance is this one. So if you will decrease this, then this FC will increase. So it will increase the bandwidth of our open loop gain op amp, open loop characteristics of the op amp. So it will increase that. So this was the relation between the compensating capacitor and the bandwidth and the slew rate. So one will ask, like, then we can reduce the capacitance and we can increase the slew rate also, and then at the same time, like, we will be increasing the bandwidth also. But the issue here is that there will be instability in the op amp, so that's why we cannot simply kept on decreasing the capacitance and then increasing the bandwidth at the same time. So that's why we have to, like, go for some trade-off. Okay, then now I will come to the week 2 lectures. So now we will come to the week 2 concepts, what we all learned in week 2. So yeah, yeah. So yeah. So in the starting of the lecture, sir told about effect of loading. He continued some lectures on loading. So effect on loading, he told. So he gave the configuration of inverting amplifier. So if you will use inverting amplifier, so what will be the effect of inverting amplifier on loading? So we will see that. So inverting amplifier, so it was basically, we have this voltage divider circuit we had. So this was this one, this was R2, this was R1. We wanted voltage across this. So if we will be using one inverting amplifier, then what will happen? This is minus, this is plus, this is grounded, this is also grounded. Okay. So let's say this is R3, R4. So this is V0. So what will happen? we wanted, this is the current which is coming from this source Vs. So this current will distribute here I1, I2. Why it is going here? Because it is getting a path to flow. Since this what we say, this path is not providing the infinite impedance, that's where the current will go in this direction also. So the current will get distributed. So this will cause loading. So when we thought, so we saw in this inverting amplifier configuration that the loading effect is there. Loading effect was there. So then how we will reduce this? But first of all, why we introduce this op amp here? We introduce op amp because we wanted gain also. We wanted, like, if this is very small, R2 is, let's say, very small. So we will have a very, the output voltage will be very less. But if we wanted to magnify that output, so that's why we are using op amps to get gain. But then we saw that if we use inverting amplifier, then gain, we, although we are getting the gain, but then the loading effect is there. Then how we will solve that? So can we use any other configuration? So let's say if we use non-inverting amplifier, okay, let's see what will happen in that. This same voltage divider we will again use. R2 is this, R2 1. So now we will give this to the non-inverting side of the op amp. So we are giving feedback from this side. Okay. Then now what will happen if current I is here? It all the current, almost all the current will go through this R2. So yeah. So yeah, almost all the current will go from R2. Why? Because this path, it is facing infinite, or in practical terms we'll say 10 to the power 12 times of ohms resistance, because this is the normal value of this impedance, input impedance of this op amp. So that's why we, whatever the voltage drop happening across R2, we will getting as the output, and this all, and in this case we can get the gain also. So this was avoiding loading effect. Loading effect. So this is good. Okay. Then you did some experiments that uh, some experiments were also there, and then we saw those, like, practically how that circuit is being realized and all. So now then the yeah, then another configuration was there, like, can we use some other configuration so that we can avoid this loading? So then we saw that if we can use a buffer. So again, if this is a gain, this is the voltage divider circuit, and then if we are using this buffer, and again after that we are using this inverting amplifier, minus plus. Okay, so this will give the gain. This will avoid the loading effect. Loading effect reduction. Avoiding. Avoiding. Okay, so this was the circuit. This was the third circuit which we used in this thing. Huh. So then now, yeah, he talked about that. Then development board kit was there. That is, I think, almost self-explanatory. But I will come to a more important topic that was discussed. That was that this half wave rectifier thing. So now we'll come to half wave rectifier. So using, or we'll say, realizing half wave rectifier using op amp. But then a question should come in your mind. The question is, why we need this? Why we need an op amp? An op amp for realizing half wave rectifier when we can use that via simple diode. So then, or we can say, why we need this, because if we need precision rectification. What is this precision rectification? So normally we know that diodes have limitation, that their reverse bias voltage is zero point 0.7 volts. So what happens then? That is the major limitation of an ordinary diode. So if we are simply using a diode, then what happens that it will give this this points and voltage will be there. So Below that, if you are measuring a circuit, or we have to rectify a circuit which is less than zero point 0.7 volt, so we won't be able to do from this. That's why we need half wave rectification. Okay, so then how we will realize that using op amp? We'll see the circuit. So we will take an op amp, it's minus. Then if we can use a diode here, giving a negative feedback to this, a load is there RL. Okay, this is V out, this is VOA, let's say VOA, this is V in, then this is it. So how this will act as a rectifier? So if this, let's say V in, or we'll say the VOA voltage here, this voltage, if this is what we say, the cathode part, this is the anode, na? Yeah. So if this is VOA, so then if this is greater than uh, the this one, the reverse by the voltage across the reverse by voltage across the diode, which is normally zero point 0.7 volt. If this VOA can overcome that, then this diode will become on. This will be short circuit. We'll say on. Okay. So then how this can happen? So this can happen. Let's say, so VOA is what? V in AOL greater than VF. Okay, this is V in, simply the op amp output equation. This we wrote here. So if V in is greater than VF by AOL, so then this diode will be on. Okay, so let's say, so for that, let's say VF, for if we take a silicon diode, it is zero point 0.7 volt for the speed. Then, and normally, let's say we take an op amp which is having 10 to the power 4 gain AOL. Then what will happen? So then V in should be greater than zero point 0.7 by 10 to the power 4. That is, that implies V in should be greater than 70 microvolt. So if we are giving a signal which is more than 70 microvolt, then this diode will get short and we can get the output. But then how we realize the half wave rectifier from this? Because if we give voltage less than this, what will happen? There will be a negative voltage here. Then it won't be able to make this diode on. So what will happen if we are giving this circuit? Yeah. So if we are giving this waveform, we input, and this is what we are expecting. This see. So this is the 70 microvolt line which we achieve from this thing, this limitation. So after this, we will get the output voltage. Okay, below that will get nothing, because this diode will be in off states. So that's how we realize this half wave rectifier. Then yeah, so we can yeah, then we came to full wave rectifier circuit. So half wave rectifier is over, then we also, in many applications, we require full wave rectifier to rectify, to convert this into AC to DC circuits. We require full wave rectifier. So how we'll realize that half full wave rectifier? So by a full wave itself, we can say, okay, for one half wave rectifier we were using only one diode, but in full wave, by intuition, we can say, okay, we may require two diodes, and we'll see how we can realize this circuit using two diodes. So let's say if we make this configuration, okay, this is grounded. This is, let's say, V input, R, R, this is R, and we give one op amp here like this. This is V naught, and this is also there. So I will tell you the working of this. So how this will be act as a how this will be acting as a full wave rectifier thing. Okay, so this will be like, let's say D1, D2. So let's say we gave uh, what's it? Uh, we gave input like this, sinusoidal input. Okay, so then in positive cycle, we will analyze first the positive cycle when Vi is greater than 0. Just for the sake of simplicity, we'll consider D1 and D2 are what? Ideal diodes. Then, when Vi is greater than 0, what will happen? Just analyze this circuit. If the Vi is greater than 0, so this voltage this will voltage is greater than this zero, this voltage. So this will be what, since this is in negative configuration, this will be negative. Okay, this output voltage will be negative, then it will make D1 on, but D2 will be off. Okay, because this D2 needs a positive supply to overcome its reverse bias voltage. So this D1 will get on. So D1 will get on. So we will have a circuit like this. Let's say this one. This is the circuit. Okay. Hmm. What happened? Where is it? Uh, so this is the circuit. So if you have any doubts in between, just ask me. uh, if you have any doubts in assignment also, then ask. I will try to solve. I will try to help. Okay. Then this is V input R, and then this is the circuit we have. So now, okay, this is connected to this. Just remove this. Okay. Yeah, this is the circuit, minus plus, this is diode, this is like this. So we have circuit like this when V input is greater than 0 and D1 is on. Okay, then we will see current cannot go through this path. Current cannot go through this path because this is providing high input, like infinite input impedance, this side of this op amp. So we can just remove this thing. Okay, this much is clear. Or we'll say just yeah. Or we will not remove. We will simply just keep it like that. So only the upper part is there. Upper part is left. So then what will happen, since this is a simple negative amplifier gain with gain of negative amplifier, inverting amplifier with a gain of 1 minus 1. So this will be V1 minus V1. Okay. So we got minus V1 here. So yeah, so this voltage, what since this was grounded, so because of virtual short this will be grounded, so this whole potential will be 0 volts. Okay, so here also we can get 0 volts. So if we use KCL or KVL equations in node A, so node A, then what we'll get, 0 minus V naught, V in divided by R plus 0 minus V naught by R equals to 0. So we get minus V equals to V naught. Okay. Yeah. Sorry, this was already minus. This was minus. This will be plus V input. So in positive cycle, we whatever the input was there, we got the output as it is. Now in what will happen? V, if V less than 0. Okay. D1 is, so we'll again realize. So if Vi is less than 0 in this cycle, in negative cycle of the input. So what will happen? This is negative. This part is negative. Then this is 0. So since then what will happen? This will become the output of this will become positive because V2 minus or minus V1. So this is, let's say, V1 or we say V1 V2. So it will be output will be V0. Output will be V1 minus or minus V2. So it will be positive ultimately. So this will be positive. है ना? So this I will remove. This was for the previous case. Ah. So now this voltage is positive. So which diode will be on? D2 will be on because this is now we are providing a positive voltage to this side of this diode. So this will be on. This will be off. Okay. We'll realize the circuit. We'll make this. So D1 will be off. D2 will be on. Okay. So then we have this one means plus diode. Then we have one resistor here in this resistor, again two resistors. Since this we remove this diode from here, we remove this thing, this path from there, and then we have this minus plus this R. Okay, resistance and Vi. Now simple, we have to use that virtual short concept and KCL KVL. We'll able to get to this get to the solution of it. So then if we see, this is 0 volt, this is also 0 volt. This circuit it will give. So if we use this let's say we use a nodal, let's say the voltage here is V. Okay, so if we'll use a KCL here at this node, let's say this is now node A. So what will happen? Node A. Okay, you can do like anything. Like you can use KCL here or here, like whatever, or you can directly do. Just for the sake of simplicity, I am just deriving each and everything. So 0 minus Vi divided by R. This and this one. This is so. This is V. This is also. This will be V. This will be V. Okay. So 0 minus V. Okay. Here also 0 minus V divided by 2R. Here two ratios are there. Plus 0 minus V divided by R equals to 0. So we will get V as minus 2 V1 by 3. So we can just make the circuit simplify as a simplified version of the circuit. We can make it like this. So this was the V. So V is the input voltage of this op amp in this non-inverting side of this op amp. So we can simply write this V is what, minus 2V1 by 3. So here we simply have that simple R, and here it is 2R, and this is the zero voltage. Zero voltage why? Because this is zero voltage here. So that's why this is 2R resistance. So I simply wrote that thing. So now what will be the V naught here? So V naught will be, this is the input voltage, and this is what, our non-inverting amplifier configuration. So the gain of that is V input into 1 plus R feedback by R, or yeah, the input resistance. So it will be what, V in is what, input voltage minus 2 V1 by 3, 1 plus feedback resistor is R, this is 2R. So we will get, what we will get, minus V1. So in the negative the cycle of the input voltage, what we got? We got the negative of the input. So ultimately it will be a positive sign, a positive that voltage. So if I summarize here, this was V input. If we say V output, then it will be in that positives, the positive cycle we got V in equals to V naught. So we got as it is, this thing as it is. Okay. But in negative cycle we got negative or negative. So it will be also positive. Okay. So it will be like this. So if we want to say, let's say what if the diodes were not ideal. So simply this will become, it will start from some voltage, 0.7 volt. Let's say if it was the zero point 0.7 volt for that op amp. Oh, sorry, for the diode. So it will, the waveform will start from this, and it will be like this. Okay, because of this. So this much portion it will. So this much portion will be removed. This is the output for practical diodes, and this was for the ideal diodes. Ideal diodes. Okay. So this we saw, and then yeah. So now we will come to clippers. So I think this might be simple. Anyway, everything is simple if we know how to solve it. So now we'll talk about the clippers topic. That was the last topic of this week. Okay. So clippers. Hmm. So clipper itself, what does clipper suggest? Like clipping means just to cut something, cut the waveform, or we can say these are used for shaping the waveforms. So these applications of shaping waveforms, we can like we may require, like if we want to shape our waveforms according to our will, or like according to the requirements or applications, we can use this clipper circuit. So again, we will be using a diode, and we'll see how we can realize this clipper, and I will show you how clippers are just or we can say half wave rectification is a subset of clippers, positive C clippers, or we can say negative clippers. Well, I'll just show you, so that way, like you can relate these clippers and half wave rectifier together. Okay, so yeah, we'll first see with the positive clipper. As the name suggests, positive clippers are what, they will clip the positive waveforms in the positive side. So we have I will just make the circuit for positive clipper V1. So we have this. A diode is here, this is there. So we have this is the voltage, like let's say the supply voltage VSS equals to whatever, let it be. So we have a voltage divider circuit, huh? And we have a pot here. This is a voltage divider circuit. We have a pot here, potentiometer, and then we have a load resistance, and this voltage this is the Vref. So basically this is the so this is V naught, this is the Vref voltage. So stage by stage I will tell you like what is actually the thing going on this clipper, how we'll analyze the circuit. Hmm. So this is diode D. So let's say uh, stage 1, we'll talk about stage 1. What happens in stage 1? We gave some input voltage V1, है ना? But now till now we don't know whether diode is on or off. Okay, so we will consider this that this feedback. Then this feedback is then the diode is the feedback is not, the diode is not properly acting as a voltage follower, because this is a voltage follower circuit, so it is not acting like that. So we'll simply say initially, when we don't know the stage of VD, so what will happen? This V reference, whatever the V reference is here, this V reference will come at this side. This will be V reference. Okay, this is VI, huh? And this is the diode. We don't know the state of this diode. Whether it is, we just check it. This is RL. This is V reference. It was V reference. This is V naught. Okay, because of this path, it came V reference came here. Now let's say if let's say VI is less than V reference, then what will happen? Since this is input voltage, the non-inverting side of the input voltage is less than the inverting side of the input voltage, input of the op amp, then this will be what, negative. Okay, so this will open, this will make this diode on, because we are supplying diode negative side to the anode part of this, and this is anode amp. So this side of this diode. So then what will happen? Then this will get short, and the op amp will start behaving as a voltage follower. So this Vi, earlier it was Vref here, but now it will not be Vref, because now the op amp started working in its voltage follower conditions. Now this virtual short will happen and this will become Vi. So we had V reference here, we had V naught here, and this was RL. So this V naught will become Vi now. Okay. So this was the case when we have Vi less than Vref. But what if Vi is greater than Vref? This this condition. So in this case, what will happen? Like yeah, we'll see. Then we, so we'll just again make it. This is Vref. This is Vi, and then this was diode. Uh, this was output of diode. This we had. This was RL. This was V reference. Okay, so what will happen now? If Vi is greater than Vref, then this will be positive. So for that, this diode will be off. Okay, this diode will be off. Then so that op amp will not come into voltage follower condition. So the output, so this will become like this. See, this open. So there is no feedback for the op amp. So this V naught. So there it is like this. So this is Vi. So this V naught we had here. So this is Vref. So V naught will become Vref. Okay. So now we'll analyze what will be the output output waveform. So this was input. This was, so let's say this was V reference. Okay. So we saw Vi less than V reference. For Vi less than V reference, this is V output. So Vi less than V, the output, the what was the output? V output was equals to Vi. Okay. So this will be like this. So this all is less than this. This is V reference. And for V input greater than V reference, for this case, V input greater than V reference, we got V output as V reference. So this will be cut down. So we see that we saw that this input voltage was being clipped off. This part was being clipped off. Now we can realize many more circuits from this we'll say from this positive clipper and negative clipper as well. So now, if we can change the V reference voltage also, so we can shift this circuit. They're like, what if V reference is negative, because negative voltage is there. So what will be the waveform? So this was input voltage. We'll say V reference was negative, let's say, but this is a positive clipper. So this, let's say it is here minus. This is V reference. Okay, that is negative. So we will get the output as this is output, this was input. So we'll get this whole circuit, we'll get like this. Sorry. I'll do the circuit this way. This is uh, so for this we output. Uh, yeah. So if this is negative till here, so we'll get only this much of voltage. This much of voltage. So all the positive side of the all the positive side of this will get cut clipped off. So this is the output of a positive clipper when we are having a negative V reference. So yeah, so in this then we have this negative clipper also. So negative clipper, what we will have, we will just change the diode position. Negative clipper. Okay, so negative clipper, we have the same circuit, but the diode position is being changed now. This is there. This is V naught. This is anyway. If you have any doubts or something, then just ask me. Don't be so silent. Yeah. So this is here. Then this is input voltage, and yeah, this we have V reference. So if we'll say what if Vi is less than V reference, first condition. So then what will happen if initial stage this was Vref, when we don't know what is the state of diode, whether it is on or off. So let's say this Vref is here, it came here. So if Vi is less than V reference, so then this voltage will be negative. So what will happen? This diode will be off. Okay. So then so this will be open. This will be open. So there will be no feedback for this op amp. So we will the output will be what? It will be equal to V reference. Now the opposite is happening with this with respect to the positive people. When we have Vi greater than Vref, okay, then what will happen? Again, analyzing this Vref is V input is greater than Vref, then this will be what? This will be positive in this that case, and then the diode will be on. Okay, so then we will have V naught equals to V input. Then it will act as a voltage follower. So how the waveform will look like? We'll see how the waveform will look like. This is input voltage, V input. Then let's say we have a positive reference. In negative clipping, we have a positive reference. So this is the positive reference. So it will clip off the negative part of that. You can remember like this also. In negative clipper we will clip the negative part, in positive part. So in this part what will happen? This was the V reference. So this will be positive, negative part will be clipped, so we'll get this wave. Okay, and the rest will be V reference. V reference. But what if we had V reference as negative? Then this will be uh, if this was the waveform, input waveform, then let's say this is the V reference. Okay, so since it is a negative clipper, this part will get clipped off. So we will get a waveform like this. This one like this. We'll get the waveform like this. minus yeah, V reference. This is output voltage. So now I was telling that how that half wave rectifier is related to this. So if we see this negative clipper, if we can make this V reference as 0 volts, if we make that V reference grounded somehow, then this output voltage will be, since it is grounded, so reference is at the ground, so this V output will get this as negative, what is it, the negative part of that input voltage, it will get that will be grounded, or there will be no output, or it will be equal to VDEF, but the VDEF is 0, so we will get no output. So this is acting as a half wave rectifier. So clipper is so basically half wave rectifier is a subset of clipper. That's what I wanted to like tell you. So now this was all most of the things all about this thing. What do you say? Uh, the topics which you covered in week two. Now, does anyone have any doubt in assignments? Any problems in assignments so that we can discuss assignment questions or any other doubts in week two or week one? Assignment. I will not tell the solutions to the assignment. I'll just give hints that will help you in solving these questions for assignment for week two. Yeah. So till now, any doubt? Just have. Hmm. If any doubts in assignment for week two, so there were some questions. What will say? So there were like good questions in that assignment. So there was some question which is I think a peak detector question, which is consisting of peak detector and clamper circuit. Peak detector, I think, yeah, you might have studied, but yeah. So there was some question on base of that. That was the first question. Then second question was on Zener diode, and then yeah. So okay, if you don't have any, anyway, I will just go through these questions just to give a hint. Okay, how they will be solved. Okay, so one of the first question was this. So we had this capacitor here, uh, diode here. This was the source. We had a buffer plus minus. Okay, then we had a diode, and this was V naught. So I will tell you why this circuit is there and why this is there. Okay, 3 volts, 1 kilohertz signal was there, and this, let's say this was V naught one, this was C1, and yeah, D2, this was D2. Yeah. So what they asked, like, I'll just so they asked, I think, about the, yeah, what will be the what will be the output signal, how it will be. So I will just say that this is a clamper circuit. I'll just give you hints. This is a clamper circuit. So, and this is a peak detector. Okay. So this is like if we'll analyze this circuit separately. So what will happen? How this peak detector works? Uh, I will say, if we give an input to this, I'll just analyze this. So this is a capacitor. So if we give an input, let's say we give a sinusoidal input to this diode. So in positive cycle, it will be short, and this capacitance will start charging. So the output will be looking like this. Let me just show you. Yeah. So this is the input voltage, and the output will be what? So till the peak of this input voltage, we, let's say Vm. Oh, I will make it little clear. Yes. Oh, yeah. So this is there. This is the input. So This is V output. Okay. So this is the peak voltage of this VM. Huh? So till VM, the since this is short in the positive cycle, this diode is on, means on. So what will happen? This capacitor will start charging. It will start charging in the first cycle. So it will start it the output voltage will be same as the input voltage. So it will keep on charging like this. So once this capacitance reaches plus minus Vm voltage, this point Vm, since we assume one thing that the time constant of this capacitance is very high. The time constant of this capacitance is very high. Okay, very high. Uh, so what will happen? Although it will get charged, but then this after this, since the if the voltage will start decreasing, but then this capacitor won't be able to discharge that fastly because of this high time constant, so it will remain there. So what will happen, this v naught will be equal to this vm, and in the negative, anyway, in the negative cycle, this is what off. So what will happen, this we will have this as the like the gain will remain vm in negative cycle, so it will keep on like this. So, although the thing is, in the next cycle, what will happen, since it will be discharged, so the input will start from here, but then since it will charge it again, so it will be like this. So, but the main point is that it will keep the voltage, the output voltage capacitor, keep the output voltage Vm. Okay, so this is the function of this peak detector. So here the peak detector is used. This buffer is just to not to load this clamper circuit with the peak detector. So that's why this buffer is being used. So you can use the concept of this clamping, and then you can find, okay, what based on this peak detection, so whatever the output coming here, it will keep this will remain like that. So but that's just you have to think how this input will behave. So you can say for first, initially this you are giving the positive cycle, so this will start charging like this. Positive cycle you give, current will be flowing like this. Positive cycle, anyway, this what we say, yeah, the diode will be off. Okay, okay, this was yeah, in the positive cycle plus minus, yeah, the diode will be off. So this yeah, this will be mm, plus minus C1, negative cycle, it will be okay, this one. Okay, plus minus. Yeah, I think this is ground. So if we talk about negative cycle, let's say start from the negative cycle. So what will happen, this diode will be closed, this output voltage will be zero, so this will be shorted, so we'll not get any output. But if yeah, in positive cycle, what will happen, this diode will be open. Okay, then whatever the input we are giving, we will get at this v naught will be that, and the same output due to virtual short, it will come here and it will come as the output of this buffer. Okay, so this will be the case. And yeah, so in that same cycle, in the positive cycle, this capacitor will also be charging. So it will charge to the peak voltage of this peak voltage of the input, that is vm. And then based on this peak detection, you will get accordingly output voltage. So this was the question one. Question two. Yeah, 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 tell me. You can unmute yourself, Pawan, or you can even write also. Hello, hello. Am I audible? Pawan, you can write your question here also in chat window if you are unable to speak. Uh, okay. Hello, hello, Pawan. You can. Okay. Can you please provide record video? Yeah. Okay. I will. I will. Yeah. I am making this. I am screen recording it. Last time, what happened? Like, I recorded this. This all those things, and then what happened? Like, because I was unable to stop the recording. But this time, I am again trying with recording, and I hope that this video get this session get recorded, and I will ask the NPTL people to share this on the forum or something. Yeah, I will. Yeah, I will do that. Okay. So yeah, this will be there. So anyway, I will upload this on YouTube channel also, and I think link maybe you won't get, but yeah, that link I will share you in the. Ah, yeah, yeah, sure, sure, yeah. So that link you will get on the, yeah, next week. I will give that link on the chat window because I haven't created that YouTube channel. So I will share that this recording there, so you can have an idea from there. But hope that this today's session, this OBS recorder works well, and yeah, 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 sure, 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 sure. Yeah. So I hope that OBS recorder works well and it records the video properly. So I'm just worrying about that. But okay. Anyway, yeah, we'll see. I'll give you the link in the next session. So yeah, question two. So question two, there is a Zener diode. So there's Zener diode. What in the reverse state, it gives the constant voltage. So which was mentioned 3.2 volts there. So we'll just write the circuit. We'll make the circuit. This is there, minus plus. Uh, so this was the circuit. I think 10K. This was the Zener diode, 10 kilo ohm. But I think it is better to attend live sessions because in that way, you have a chance to ask whatever you want to. So that is because anyway all the recordings are all the lectures are recorded, so you won't get a chance to interact. So that's it. Yeah. So this was the. So we were asked to tell about the output voltage in this case. So uh, what will happen? We'll have to check first what is the state of the Zener diode, because this like little uh, different from the normal circuits what we have. So here it is there. So if Zener diode, so how we'll check this whether it is on or off? So that is simple. What we will do, uh, we have this V2 was 1 volt. Okay, so V2 was 1 volt. So here this is 0 volts. So whatever the thing, this will be negative. Since we are giving a negative potential here, 1 volt here, which is greater than the non-inverting side of this terminal. So what will happen? This will be negative. Anyway, this is a non-inverting configuration. We get the negative output. You can say from that also. So since this is negative, this output will be negative. So this Zener diode, we are applying basically negative to this side of the Zener diode. So what will happen? This will make the Zener diode reverse bias. Okay. So when the Zener diode comes in reverse bias, it acts as a potential source like this. है ना? So this will be 3.2 volts. This is 10K. This is 10K. This is 1 volt. We already have one more feedback of 10K. This is minus. This is plus. Okay. Hmm. This one. Then now we have the circuit. Now it looks although yeah, it looks although simple, but then there is a this potential. So potential source is uh, in the feedback path. So normally there is a concept of super node. You can use that, but if you don't know, there is also an alternative way to convert this whole thing into voltage source, and then current source, then again convert it into voltage source. So how we can do this? So just I'm telling you how to solve this little not yeah, little complicated feedback circuit. So we have this. So these are the tricks which when you practice a lot, then you come to know, okay, we can do like this also. So like this is 10K, this is 10K, This is what 3.2 volts. Okay, so now in order to simplify this thing, what we will do, we can change this is to current source. So how it will be, it will be like this: 10k, this will be 10k, this will be a current source, and since the direction is like this, so it will be like this. But what will be the voltage of this? This is the voltage, this 3.2 divided by the parallel combination of these two resistors. Okay, that is 10k, 10k parallel to 10k. Yeah, might is not, yeah. 10k parallel to 10k. So this is the value of this current source. From here, like this simple, this is the parallel combination of 10k and 10k. You can get 5k. So this will be like simple one 5k resistor in parallel with the current source of this value. Let's say I1. So you can simply use this circuit in this, whatever the input and output were there, you can use a KCL or KVL here and you can get the output. Okay, this is simple. After that, so there was one, yeah, there was one theoretical question that I think you can get by seeing the lecture. I'll just focus on the practical questions. Then there was question 5. Question 5 was there. So question 5 was having two diodes, and they asked to show the like what will be the output, or I think something like that. So I will just draw the circuit for you. I'll just make, I will just tell you how to solve this. Plus minus, this was the circuit. Hmm. So whenever you get a circuit, like whatever the circuit it is, just analyze like why those op amps are there and why in what configuration they are. Are they in inverting configuration? Are they non-inverting configuration? Are they in differential? Are they acting as a differential amplifier? Or are they acting as a summer amplifier, differentiator, integrator? So that's why like these topics are being taught you separately, so that you, when the circuit, complex circuit comes, so that you can use all those concepts, and then okay, you can like, you can bifurcate a one particular question into pieces and then solve it, then it will become easy for you to solve. Okay, so here also like what they give, like if you will say like every big circuit is a like combination of small circuits. So if we are able to know okay which part of that circuit is used in that, like what is the part in that differential or non-inverting inverting amplifier, then things become easy for us. Okay, so like in this case, yeah, in this case, like although this was easy, but since the feedback part was little complicated, so we break that and we make it simple. Okay, similarly like we do things. So here like okay, so this is D1, this is the input. So then, yeah, 12K and 10K. So first, we will have to ensure whether the uh, this feedback part is there or not. Like whenever you get a diode in the feedback path, so you will have to ensure whether the diode is on or off. If it is off, then the feedback part will not work, and so that op amp, that virtual chat and all those concepts, we cannot play with those concepts. So first you will have to clear the question with that, whether this the diode in the feedback, or whether the whatever the diodes are in the circuit, whether they are in on or off state. So for that we'll first ensure that whether D2 is, this is D2, yeah, this was D1. So whether this is on or off. Okay, for that we know D1. So if we say V input is greater than 0, so we know one thing, that D will be on. For V in less than 0, this will be off. Okay, so when V in is greater than 0, we know that D1 is on. Then, yeah, now we have to comment on D2. So let's say, this this is, let's say, V2, this is V3, this is V1, and just seeing like saying, giving the names to the nodes. That's all. So what will happen? This is first part. So this is on. This, since this was the ideal diode, so we will have V1 as the input. Okay, but what will be V2? Now, uh, you may think, okay, what is there? What, like, is this complicated or what? Like, so you can simply pull that circuit out and we'll see. This is simply a voltage divider circuit. So things will become easy for you. So this is V2. So what is V2? Normally what we give V1 is V2 is V1 into, this is, let's say, R2 and R1. R2 upon R1 plus R2. This is this. Okay, so we know this voltage. We will get this voltage. So now V3. This V3, since we don't know whether this diode is on or off, so what we'll do, we'll just so now if this feedback is not working, then 0 volt will be there here initially, है ना? So then V2 is here. So if so we know that V2 is anyway, the input is positive, so this will be positive, greater than 0. So it will be obviously greater than the 0 volt which is here. Okay. So what will happen? The non-inverting side of this op amp is greater than the inverting side of this negative terminal of this op amp. So this will be positive. Output of this op amp will be positive. Okay. So then this diode, this side of this diode is facing the positive output, so this will become what, on. This will become on. Okay, so this process made us gave us an idea. Okay, this diode was in uh, D2 was in on conditions. So I'll just add some pages in this. Add, let's say 5 pages here. Okay. So this showed that D2 is on conditions. Now I think you can solve this circuit. This circuit becomes really easy. So I'll just make the circuit for you. This is there. Okay. This is op amp minus plus. This is again. This is diode, and this is input. So D1. This is also in positive cycle. This is on. Anyway, I will keep it like this, because negative it is open. So accordingly, you can make that circuit. So this is now very easy. In positive cycle, it will be simply this circuit. Simply you can use KCL, KVL, anything from there. Okay. So this was the question. What was this? Question 5. Yeah. So question 6. Question 6. So okay, that was also a simple question. Question 6. So we had a configuration like this, minus plus. So this is there. Okay, one diode was also there, and one diode was here, and this is okay. Uh, yeah. So this is the input, 1K, 1K. This is there, 1K, V naught 2. This is T2. This is T1. This is V naught 1. So now we were given that V input is 4 VP. So again you have to think which diode is in what condition. So you will see that V input, that is like in positive. So you gave a positive voltage which is in comparison to this 0 volt which is here. 0 volt which is here. So that is like this voltage is greater than this voltage. So since this is the negative terminal voltage of the op amp, so we will get a negative output. So then what will happen? This diode will get on. This will be off, or this is in forward bias. This is in reverse bias. So from here you can then the circuit is easy. You can get V naught 1 and V naught 2 accordingly. Okay. Then there was a question voltage follower, like, can it be used in which in what type of circuit? So there were like options. So you can see, you can just check the circuits of these active filters, sample and mode circuits, whether the voltage follower is being used or not. So I think if you know the basic concept of this voltage follower, like why it is used for this isolation circuits, isolating one circuit from two, or reducing the loading effect, like those things, it is used for that. So based on that, you can simply answer this question also. That's a question 7. So then there was question 8 was okay. Question 9, question 10. Question 10 was simply this. What will say? That is a full wave rectifier. Okay. Then I think in question I will just tell you write the question 10 for you. So this is there. This is 1K. This was the going into this minus plus. This is uh, 1K. 1K. This was diode. So I think what we studied in half full wave rectifier. So yeah, what I thought it is correct. Yeah, so here only the diode directions are reversed. So how it will affect the output voltage? So here D1 is D1 D2 is there. So I'll just help you with this minus plus. This is there. Okay, this is 2K. So this diode's directions are reversed. So what will happen? But what we studied in full wave rectifier, diode directions were in downward direction, like this. Okay, it was like this. So you can like intuitively also say what will be the output, at least at least the shape of the output, how it will go in with one direction, just by like what if you change the reverse, if we reverse the direction of the op amps, like you can say from that, or otherwise you can, if you want to solve the this full like circuit, then you can simply solve using that thing, like the full wave rectifier thing which we used. So based on that also you can solve that circuit. Okay, so that will not be an issue in this part. So this was all about the assignment questions. Now I have some questions which will say some extra questions. So these will help you like centering your concept, and like these are like somewhat similar questions, but like it will give more idea about, okay, what how to solve these circuits and diode circuits which are used in op amps and all. So one such question is this, like an op amp with the precision rectifier circuit. As I told you, this op amp configuration we use as a precision rectifier circuit. So so they are using the ideal diodes. So output saturation levels for this. So once you read this question, so assume that when conducting diode exhibits a constant voltage drop off. Okay, that is ideal without. Oh, okay. Op amp is ideal, but not the diodes. Diodes are having drop of 0.7 volt across it. So this drop is having 0.7 volt. Okay. So we needed what? V minus V naught VA. This is V minus, this is VA V naught. So what will be the values based on these parameters? And there was one more question in that, like if we input square wave with 1 kilohertz frequency and 5 volt amplitude, so what will be the output? So this yeah, so what will be the output for that, this question? So just go to this question. Hmm. So yeah, I will tell you about this. So what happens? Like let's say we consider first part. A where V1 is 1 volt plus 1 volt. Okay, so this is also like a simple half wave rectifier, but yeah, we'll see how. Since the diode is not ideal, so we'll see how to combat that diode, like which is not when it is not ideal. Okay, so we'll see. First, we'll see whether the diode is on or off. So when we give V1 1 volt positive voltage, so since V minus initially, when we'll see if the diode is not, we don't know the conditions of this diode, then we will simply consider that this feedback is not working. So whatever the 0 voltage is here, it will be right now, it will be here. So V1 is greater than the 0 voltage. So what will happen, the output will be what? If the positive non-inverting terminal voltage is high, then the inverting terminal, the output will be positive. Okay, so output will be positive. This is, I am talking about the first case, V1 equals to 1 volt. So for that, this diode will become for forward bias. Will be forward bias. One question I have to ask, like, if V1 would have been point, I think then yeah, then also it would have been wrong. Yeah. So this is there. So D is in forward bias. Okay. So now we can utilize the negative feedback part. Now we can utilize the virtual short concept of this op amp and all these things like virtual short and all the feedback circuit, because now the op amp will look like this. Simply, this is positive, this is negative. Input we are giving to the non-inverting side of the op amp, and this is acting as what? Non-inverting terminal, non-inverting gain op amp. Okay, this is R, this is R, this is like this. This is the diode is shorted and we have one load resistance RL. This is V0. So now this is a simple circuit. You can solve, okay, what is so V minus was this. So what will be V minus, since now it is acting as a negative feedback amplifier. So V minus will be equal to V input, that is 1 volt. Okay, and what will be the output? Output will be simply the gain of the non-inverting amplifier, 1 plus 2, 1 plus what feedback is R by R. Okay, so that will be there, that is 2 volt. Output will be 2 volt. And but what will be VA? So VA was here. This was VA. Oh, okay, this will be like this. It will be like this, 0.7 volt. Since this is not ideal. So VA will be what? So simply to solve VA, we can have this. V naught, this is VA and V naught is 0.7 volt. You can use a KVL equation here. VA, we are going in this direction. Since a drop is there, we can say minus 0.7 equals to what? V naught. So VA will be what? V naught plus 0.7. So V naught we know 2 volts, so it will be 2.7 volts. So how to check this answer? So we say V naught is 2.7 volts. So V naught, since 2.7 volts was being provided to this diode 2.7 volt was being provided to the diode. That's why it was able to overcome this zero point 0.7 volt and finally we got the output 2 volt. Okay, this by this way we can see, because if this voltage was coming less than the output voltage, then there is some calculation error in your KVL equation. Like, because I've seen many people are like using this KVL equation wrongly. They don't know like sign conventions, how to use it and all. Okay, this, so similarly we can go for 3 volt also. That is simple. Instead of 1 volt, only these values will change. But what if we'll just consider about the negative thing, negative minus 1 volt. So in C part we have V input as minus 1 volt. Okay, so what will happen if we give the negative voltage? So if we give negative voltage here, I will just clear it for you. Just clear it. So if negative voltage, again we will compare, we don't know the state of the diode, whether it is on or off. So now, so this feedback we don't know what is going on this feedback. So we'll consider this 0 volt. So this minus 1 volt is given to the non-inverting side of the op amp, and this is 0 volt. So what will happen? It will give negative output. Okay. So negative output will give, so that so what will happen then? This diode will become off, because negative input is given to this diode. So D will become off. So if D is off, then there is no output for this op amp. So this op amp, it will act like this. This is V naught and this is V input. This we had this circuit like this. It was connected here, and this is R. This is R. This is, yeah. This was V minus, and this was load resistor RL. So now if you will see, if you will say that this, so what will be the output voltage now? So since this op amp output is not connected, that means it will not, this will not act as a proper like feedback, negative feedback circuit, because feedback has been cut from it. So what will happen? This negative circuit will not work. Then negative feedback path will not work, and this we cannot use virtual short here. Virtual short cannot be used here. So this V input will not be equal to V negative. Okay, so what will happen? V output will be equal to 0 volt equal to V minus. So this will be 0. So no current is flowing from it. So we cannot do virtual short here. That is what negative volt or minus 1 volt condition was there. Okay, so similarly you can go for minus 3 volts also. Now, in one more part was there. Also, find the average output voltage obtained when V in is a symmetrical square wave. Just we'll see what will happen in this condition. Okay. So we have an input. Let's say this is the E part. We have an input which is like this, symmetrical. What we get from symmetrical, that is like both positive and negative both are there. Plus Vm and minus Vm is there. Okay. So now what will happen? We saw in positive voltage when we are applying, it is giving output, but in negative side it is not giving output. है ना? So for positive, so only for positive it will give output, but in negative cycle it will not give output. So it will be like this. Okay, so this was 5 volt given, minus goes to minus 5 volt. It is given in the question. 5 volt amplitude and zero average. Zero average means that symmetrical it was. Okay, this is having zero average. Zero average. Okay, yeah. So this will be the output. So, but what will be the output, since we know this in the positive side of this will be acting as a simple this circuit like this. Okay, so what was V naught? V naught was this. We got V naught from this V1 into 1 plus R by R. So it will be 2 times of the input voltage. So we'll get plus 10 volts, 10 volts, and this will be 0. Okay, 0. Yeah, this one is 0. This is 10 volts. Clear. Hmm. This is the output. So then, since V output is V input into 1 plus R by R, which is which will be 2 times of V input. That will be 2 times of 5 volt. That will be 10 volt. So this will be 10 volt. So now you think this circuit was giving a gain of 2, and what this circuit gave, this circuit did with a square wave. So if for some applications, if you need this square wave to be not symmetrical, like you want to shift to give the DC gain of this circuit, get DC gain to this input voltage like this square wave, because here the DC bias is what, 0 volt. If you want to shift it to the like upper value or what, so then you can use this circuit. So this what the circuit did, shifted the DC gain, or let's say the DC offset to the 5 volt. So that is symmetric. Say the output wave was now symmetrical about 5 volt. Okay, so that's why like we should when once we get the answer, we should see, okay, why this how this output will help you like in real scenario when you will go. So if you want to shift a waveform from you want to shift the DC bias of that waveform, then you can realize these kind of circuits. So you can think in this way also. So yeah, we'll move to the another question. Okay, just read the question once. The op-amp in the circuit of figure this is ideal. The output saturation levels are given. The diodes exhibit a constant 0.7 volt drop when conducting. So here also this they have given a, what we'll say, uh, this one, non-ideal diode. So we again have to get V minus VA V naught. So so now you can get an idea of, okay, if one diode is there, okay, somehow full rectification can be done. So what we saw in this previous question also. So you yourself you should think like, okay, if okay, two diodes are there, then maybe it is giving the full wave rectification. Okay, so yeah, just analyze the circuit. So if you have any doubts, you can ask me. Like not apart from this, like anything, any other doubt, anything apart from this, you can also ask. Yeah. So yeah, I'm just the person who joined. So I'm just discussing about this question. So you can just go through this question. So these are the extra questions which will give you an insight about. Um, it will strengthen your concepts and it will give you insights about, okay, how these questions are solved which are involving diodes in an op-amp circuit. So yeah, just go through it. So now in these cases we have like non-ideal diodes. So we have sequence and moving. Uh, so yeah, I will just solve this thing for you. So what is happening? So we have to find V minus VA and V naught. Okay. So we'll see. So first again we have to see like what are the states of these diodes, these D1 and D2 diodes. Okay. So for that what we'll do, we'll consider the first case when A equals to Vi equals to 1 volt. Okay. Then we'll see okay what how this circuit will behave. We'll first analyze. You may have some answer in your mind. You can just share if you want to the chat window. What will be the condition of D1 and D2 when we are giving a positive volt here? Vi input. Okay, input. Yeah, this is the circuit. This is R. So let's say we give positive input. This is 0 volts. Again, we don't know about the condition. So we'll just since this is the we are giving a positive supply in the non in the inverting side of the op amp, then the output will be what negative. Okay, so it will reverse, it will give a 180-degree phase shift to the output. So that's why this output will be negative. So then if negative supply is given to D2 and a negative supply is given to D1, so what will happen? It will reverse bias this thing, but it will at the same time follow by this thing. So how the circuit will look like? It will look like this. Since this is what we say non-ideal diode, so we'll have this. Okay, this is R, this is uh, so this will be open since this is in reverse bias, and this will be grounded, and we have this R. So just get an idea, just get a feel, okay, how you will approach a question like so for that you will have to realize how what are the states of diode, how the circuit is behaving, what are the parts used in that op-amp circuits, and how you can separate them and separately analyze and then combine finally to get the final answer. Okay, so in this case, what we got punch and board was there. So this was open. So what will happen? This path is useless. This path is useless. No current will flow from this, so we can remove it. Okay, we can remove this path. Only we are left with this circuit. So, but output was here, V naught. So V naught will be what, 0 volt. Will not get any output here. Here. Oh, no. It will not be. Yeah, it will be 0 volt. Sorry, it will be 0 volt. So here also we wanted VA. We need to calculate V and V minus. So since this is virtual short, so V minus will be also 0 volt. Okay, but what will be VA? Simply we can use a KCL here. V minus 0.7 equals to VA. So V minus is 0, so VA what it will be minus 0.7 volt. So it is simple. Okay, so since we know the state of the diode, we can tell about the tell about the how the circuit is behaving. Now 3 volt it will act similarly. We'll see of minus 1 volt how this circuit will act. So when the input, let's say I will take C case when input is minus 1 volt, negative input we are applying. Okay, so you can yourself like think which diode will be acting and how why it will be acting like that. So this is the circuit. We have V naught here, we have VA here, we have this here, and this is V minus, this is R, this is VI. Okay. So this was the circuit. Now we have to analyze how this diode will behave. So again, we gave a negative voltage here, negative voltage in the in the inverting side of the op amp. So this is 0 volts. So what will happen? The output will be positive. It will be positive. So what it will do? It will make this thing forward bias, but at the same time it will make this reverse bias. So how the circuit will look like? Let's see. Just one question: what if there was this thing was not grounded? I'll just ask you one thing, just to I know no one will reply, but still I'll ask. If this was 2 volts, what would have happened then? Can anybody tell me? Because I gave 1 volt here, this is 2 volts. What will happen in this condition? Just think. If you want to write in the chat box, you can write. If no, anything, I'll ask like this. Then, what will be? Yeah, simply what will be the condition of D1 and D2 when this is 2 volts and with the input is 1 volt? Because we saw when this was 0 volts, so we got this to be forward biased and this to be reverse biased. Hmm. And this was, yeah, minus 1 volt. So what will happen in this case? I will tell you. This is 2 volt. This is yeah. Actually, this so find the what. So this is what we give the output of this as V. This is V2 minus of this. This, let's say V1. So V plus minus of V minus. This is the differential output now. So what will happen? This is 2 minus of minus 1. So it will be positive only. So the same thing will be happening. Like D1, D2 will be forward bias and D1 will remain in reverse bias. But what if this was not 2 volts but let's say minus 0.5 volts? Then what will happen? If you use this concept, then what will be the state of D1 and D2? Okay, so what will happen? See, uh, what will happen? This P plus is what? Minus 0.5. This is what? Minus 1. This VD. So this is again positive. Again D2 will be in forward bias and D1 will be in reverse bias. So this is positive again. This output will be positive. But what if this was minus 2 volts? Now what will happen? Now this is easy to answer. Hmm. So in this case, what will happen? This is minus 2, this is minus of minus 1. So ultimately, we will get a negative output. So this will become negative and D2 will become reverse bias. So that's why this positive side potential is also very much involved in deciding the states of this D1 and D2. So you should also you should know when you are solving this type of questions. Okay. So yeah, this was little deviation from the main question. So yeah, what we were doing, the input voltage was minus 1 volt, and yeah, I'll just remove this. Ah. So this was grounded. Minus it and conjugate for this period. Yeah. Now, this is grounded. This is minus. This is plus. Okay. Yeah. This was the configuration. So this D2, so we gave minus volts since this was 0 volts. So what will happen? This will be uh, negative, but this will be positive. So this will be forward biased, but this will be reverse biased. Okay, so the circuit will be looking like this. We don't have this one, but we have one op amp, one plus minus. Then we have this V naught. Then we have this one, R is here, V input is here, which is minus 1 volt, and this is R. Okay, so this feedback we don't have D1. This is minus, this is plus. Fine. So this is 0.7 volt. Okay. So then, so now this is simple. This is a simple circuit. This was VA. So you can get V naught as minus 1 off. This is our inverting gain amplifier. R by R you will get 1 volt. Okay. So this will be 1 volt. And what will be VA? Again, VA minus 0.7 equals to V naught. So what will be VA? VA equals to V naught plus 0.7. That will be 1.7. That will be VA, and yeah, V minus will be 0. V this is 0 for the virtual short. So this what they asked about, V minus VA and V naught. So V minus 3 volt we can do similarly, minus 1 volt we can do similarly. Difficulty will come when when they will attach some source here, some potential here. Then you will have to think which one is greater and how then the output will react. Okay. Then yeah, there was one another question. So just see VTC, by the way, that is the the relation between the output voltage and the input voltage. That we say voltage transfer characteristics. So that is the relation between the output voltage and the input voltage. So these relations are sometimes it is important to analyze how the circuit is behaving when we are giving a certain input. So that's why this VTC is required. So just go through the question. Give some time. So here also the diode is not ideal. It is having some potential. And this is, by the way, yeah, this is the input voltage. The gain plus minus 3 volt, and as the same time we will not up to the RC stabilizer plus minus 5 volt. So they are asking for advantages and disadvantages. So yeah, that is there. So how will solve this? And what will be the VTC? So we have input voltage, and only one diode is being used here. So so we have to determine this thing. So yeah, I will solve this question. So what is there? Uh, so VI, we will analyze it for 3 volts. Okay, we will analyze it for 3 volts. So what for 3 volts, and we know VDCM is this. So what is this? See, let's say VI is 3 volts. So what will happen? Like this thing. So this is positive. This is 3 volts. It is giving here, and we will see this is 0 volts again. So this output of this OA2, what it will be? It will be negative, since this potential is more than this side, the non-inverting side of the op amp. So then what will happen? This is negative. So then uh, this circuit will become open. This will be in reverse biased. Okay. So D1 will be off. This will be off. So I'll make a circuit for you. So how this circuit will look like? So first case, V input is 3 volts. Yeah. So then this circuit will look like this. This plus this R R. This is input voltage and VI, and we have resistor from here. This is R, and this will be minus plus, this will be open. So this circuit, this op amp will not work simply. So since this op amp will not work, so we cannot say the virtual short concept will be there. So this is 0 volts, so we cannot say this is also 0 volts. Okay, so because this is not acting as a, this is not having any negative feedback. So then what will happen? So this potential, if we go, so yeah, so we have this, so we have some input vi. So how we'll solve this? So basically we are giving, we can simplify this by saying, uh, yeah, we can simplify it by saying we have given a, so yeah, we can, this is plus minus volt, one here and one at this also. Okay, 3 volts. This is also 3 volts. So this circuit is not there. So what will be there? So this is, so since no current can flow from this, so this will be 3 volts. Okay. So here also because of virtual short, it will be 3 volts. So what will be V naught? Since this is 3 so no current will flow here. So the output will be, it will be equal to 3 volts. Simply simple. Okay. Then yeah, then we have in our question for minus 3 volts also. What will be the case? So Vi equals to minus 3 volts. How the circuit will behave? So now we just clear this thing for, clear this thing here. Yeah. So in minus 3 volts when we are giving, so this is minus 3 volts. First we'll analyze how this D1 is acting. So this is 0 volt. This is 0 volts. Okay. So then so this is 0 volt, so this is negative. So negative voltage is given to the negative terminal of the op amp. So the output will be positive. So then this diode will be in what, forward bias. Okay. So now how the circuit will be looking like. This, and since this is a non-ideal diode, so we will have a like a drop of 0.7 volt at the feedback. We will have this minus plus, and this will be this, this will be R. Okay, this will be R, this will be R, minus plus, this will be this one. Okay, so this we are giving as minus 3 volts. This is V1. So now here, so we can now, since this is having a negative feedback involved, so this will, the virtual short concept can work here. So this is 0 volt, so this will be 0 volt also. So this will be also 0 volt, so this will be also 0 volt, 0 volt. Okay, so we have 0 volt here, so we can use a nodal equation here, nodal at this A point. So if we use nodal voltage equation, nodal voltage equation at voltage, node A, then it will be 0 minus of minus 3 divided by R this side. We'll go this side also, this will be plus 0 minus V naught by R equals to 0. So what we'll have, we'll have 3 equals to V naught, 3 volts. So so whatever input we gave, so we observed that the output was constant. So so what we can say the advantage of the circuit is, like by using only a single diode and whatever the input we were giving, so we were getting the same. So let's say if we were giving 3 volts here, then again minus 3 volts here. This is the input voltage. If it is a square wave, symmetrical square wave, then what will happen? The output will be a constant 3 volts.
So it acts as a full wave, kind of full wave rectifier without uh, what will say, without realizing two diodes, without realizing two diodes. Okay, so that is like yeah, that is advantage of silicon. Similarly, we can use 2 for minus 5 volts also. So this was for today's, like we don't have time for these other questions. Just go through what we did, what all we did today. So in this session, we discuss about like there were some previous session topics like how this compensation bias, like how this bias current behaves and what are the compensating and how this compensating technique is like helping and removing that bias current. So we had this op-amp configuration. So IB1, IB2 was there. We gave the input voltage, and then we came to know that this thing was extra. Okay, R2 IB1. So use another. So this thing was extra. So then we have to remove this because this is the actual voltage. This is the actual output voltage which we needed. Okay. So for that we used a resistor here in the non-inverting side of the op amp. By using that, what happened? Like after the final calculation, we were able to. So what we thought to the output voltage to be zero, we came to know that R3 should be R1 parallel to R2. This we came to realize this. So that's how we can, and but one assumption was there like IB1 should be approximately equal to IB2. If these two are not equal, then although compensation will be there, but the thing will be that it will not be the it will not be able to compensate fully the bias current values. Okay, but still compensation will be there if these are not equal. But here we assume okay, if these are equal, then R3 parallel R3 equal to R1 parallel to R2 it will work. So then we saw that what is the effect of slew rate on the bandwidth. So same we know that slew rate is like the change of the voltage with respect to time, and we know that that change is given by the current and the divided by the capacitor. And all the op amps are having compensating capacitor. So that's why that open loop they get that open loop characteristics of this thing like low pass filter. So this which where the cutoff frequency is being decided by this compensating capacitor of the dopant, which is inbuilt in that. We are not supplying externally. So that was the case. So there like we use this thing, and then we came to know that since it will reduce this capacitance, then this load will increase. So but it will reduce the capacitance, then this cutoff frequency will increase. So we will get high bandwidth, but it will leads to instabilities in the program. So that is a trade-off which we'll have to uh, we have to think, we have to consider. So there was some loading effects in inverting amplification. We saw that loading effect was there. In non-inverting, it was not there. Then we use a buffer also to use non-inverting amplifier. Oh, sorry, inverting amplifier with the buffer, so that we can use inverting amplifier because inverting amplifier gives high gain in respect to non-inverting amplifier because it is one plus for non-inverting it is one plus RF by R. It is not the case. Yeah, it is not the case. But yeah, we saw that okay, buffer is the buffer. We are after using buffer, we can use this non-inverting amplifier thing. So then we use how this half wave rectifier amplification is done. Then we saw the full wave rectification. Then yeah, we analyze those circuit. Then we saw then we saw this clippers, positive clipper, and how this is acting, and how the half wave rectifier is a subset of positive clipper, and how this negative clippers also work. So we can clip the negative, we can clip the negative side of the waveforms. Okay. So then we discussed a little bit about the assignment questions for this assignments of week 2, and then yeah, so these were the questions and all. So thank you, and we'll meet in the next session. That is next week Tuesday. We discuss more about these questions. So yeah, we'll meet in the next week. Tuesday same time, 6 to 8.